Hi everyone. So today we'll be discussing the solutions of IOQM 2021, and after we have discussed all the questions, we'll be presenting an analysis of the paper, which will hopefully be useful. So let's begin with the first question. Also, this is the year in which there were only 12 questions, and IOQM and INMO was basically combined, so there was just one paper. So you'll only have 12 questions in this paper. I'll be doing 6 questions, and then Siddharth will be doing the other 6 questions. Okay, so let's begin with problem one. Three parallel lines, L1, L2, L3, are drawn in a plane such that the perpendicular distance between L1 and L3 is L1 and L2 is 3. So it's like L1, L2, L3. You have this distance as 3, this distance as 3. A square ABCD is constructed such that A lies on L1, A, B lies on L3, and C lies on L2. Find the area of the square. So basically, to find the area, you need to find the side of the square, side length. Also, maybe some of you people would be wondering why I had drawn the square like this, like a tilted thing at an angle. So the reason is, like, if you draw it, let's say like this, then you know that the angle ABC should be 90 degrees, right? So C would lie on L3 only. Like if you draw AB as perpendicular, then C dash should lie somewhere on L3, which is not true according to the question statement. So like you have to draw it an angle theta such that once you take a perpendicular and these two lengths are same, then C will lie on L2. If you want, you can complete the square. Okay, this does not look like a square for now, but we can assume it does not really hurt. The thing is, the point D is not really useful for us for now. We'll see why. So one idea whenever you see a geometry problem is like to see some nice perpendicular, especially when there's a length involved. Like to use lengths, like if you have to calculate a length, you'd probably like try to find a perpendicular. So let's say I have to find BC, right? So like my idea would be to like find some right triangle, let's say like this. Let's call this point a C dash instead. Such that if I know this length and I know this length, then using Pythagoras, I can find BC, right? Or even if not a right angle triangle, you can find some triangle in which one angle is known. Then you can use cosine rule to find that length. So in this case, since we have like three parallel lines and we have a lot of 90 degrees, it's sort of motivated to define these perpendicular lines, okay? So like I drop this perpendicular at B dash and this perpendicular at C dash. Then we can chase some angles and see like, excuse me, if this angle is theta, this is 90 minus theta, this is 90, and these three angles should sum up to 180 degrees. So this angle will also be 90 degree minus theta. So now it's pretty evident that triangle AB dash B is similar to triangle B C dash C. This means AB dash over BC dash equals to AB over BC. This should probably be CC dash AB dash B similar to BC dash C. Okay, this looks correct. And this should be equals to B dash B over C dash C. Okay. So now let's put in the lengths we know. Let's say that side of the square is X. So AB dash is 6 over BC dash. We do not know yet, but since this is a right angle triangle, we can probably use like some trigonometries, like tan theta is BC dash over 3. So BC dash is like 3 times tan theta. This is equals to AB, which is X, over BC, which is also again X. And this is equals to uh, B dash B, B dash B, over C dash C, 3. Oh, okay. There's a better way to do this. Like, instead of similarity, you can just see that these two triangles are congruent because the hypotenuse are equal, like AB equals to BC. So by RHS rule or whatever you want to say it, this is just equals to, these are just congruent. Yeah, this is probably better. So this gives you AB dash by BC dash. Like you can see from here also similarity. It does not really change it. You'll get that 6 by tan theta, 3 tan theta equals to 1, which means tan theta equals to 2. Okay, so now we know this theta, right? Uh, Now, so tan theta is 2, right? Which means that this side is 6. So now using Pythagoras theorem, BC square must be equals to, 6 square plus 3 square, which is 36 plus 9 equals to 45. And we wanted to calculate the area, right? So area is just side square. This is just 45. And this is what we wanted. So the area is 45. That's the answer. Okay. So I hope that was clear. So the main idea was like finding these two congruent triangles or even similar. That does not really change the solution. One of the solution which I myself did when I was giving this exam was coordinate bashing this. Probably not the best idea, but what I did was like set this up as 0, 0, and you know that this would be like -6, x, and this would be like something x dash, -3, and then you equate these two lines to find one relation between x and x dash, and you can probably somehow find the other relation as well. Oh yeah, and I involved this D point as well. And you can basically show that if you consider this parallel line by symmetry, that this distance should also be 3. And it's very complicated solution, so like not really recommended. But anyway, I hope the similarity solution was clear. Okay. So this is the second question. Ria writes down the numbers 1 to 101 in red and blue pens. The largest blue number is equal to the number of numbers written in blue, and smallest red number is equal to half the number of numbers written in red. How many numbers did Ria write with red pen? Okay, so one naive approach can be like this is not too many numbers, right? It's just like 101. So what you can try to do is like you can see like, okay, how many blue numbers are there? Let's see one blue number when only two blue numbers are there, when three blue numbers are there. And like you know that there will be like 100 red numbers, 99 red numbers, so on. And you can try to manually do this. But obviously that's not like the best way to do this because what if this number is too large? Won't be the case in IOQM, but still. So the thing is, we are given largest blue number is equal to the number of numbers written in blue. So let's say there are X blue numbers. So, you know, it's like 1, 2. Okay, maybe we can do it in a nicer way. 1, 2, 3, so on till X minus 1. And then this number is written in blue. X plus 1, so on till 101. So, and okay, smallest red number is equal to half the number of numbers written in red. So let's see how many numbers will be in red. 101 minus x over 2. Sorry, 101 minus x are the red numbers. And smallest red is 101 minus x by 2. Okay, now notice that from this information, largest blue number is equal to the number of numbers written in blue. So we know that this is the largest blue number. Like all these numbers will be red. None of these can be blue. So we can just like mark these with a red pen because we know these are red. And these are a total of X numbers. The significance is if let's say some of like one of this number is red, let's say if 2 is red, then how many numbers are there from 1 to X? Only X minus 1. There will be less than X numbers. But we know that there are X blue numbers. So there cannot be any red in this area. So which means that all of these numbers are blue as well. So like the first X numbers are blue, and then the next 101 minus X numbers are red. Clearly, this is the smallest red number, right? And what we know is this is also the smallest red number. So 101 minus X over 2 equals to X plus 1. And you can easily solve this. So this will give you X as 33. 33. Yeah. And it says, how many numbers did Ria write with red pen? So this is 33. This is 34. And the number of numbers written with red pen is twice of this. It's just 68. The answer is 68. The main idea was trying to recognize this thing that the first X are blue and the other things are red. Okay, I hope this was clear. Let's move on to the next question. This was a very easy question. Like, I don't even know why they made the statement so like look so complicated. Like, this is like a very weird sentence. Anyways, so let's see. Consider the set T of all triangles whose sides are distinct prime numbers, which are also in arithmetic progression. Okay, so it's distinct prime numbers, and that is in arithmetic progression. Let triangle. Okay, so once you see this thing, like the very basic thing which pops up in your mind is 357 triangle, right? So you know that this triangle belongs to T. Okay, let's read further. Let delta belonging to T be a triangle with least perimeter. Okay, so we are talking about delta, right? And we have to see the triangle with least perimeter. So we know that the perimeter of this triangle is 12. Oh, sorry, 15, which is very small already. The 15 is a small number, right? So intuitively, this should be clear that this is probably the least like triangle with the least perimeter. But if you're still not satisfied, you can like try to manually find another triangle if you want. Like, so what you can do is you can take another prime numbers, like smaller than 15, obviously. So I take these prime numbers and try to form a triangle which is a perimeter less than 15. So now see, if I take a triangle which has side length 13, the minimum side length the other side can have is 2. And this triangle already has perimeter greater than 15. Sorry, equals to 15. But this side will be like a non-zero number, positive. So it will be greater than 15. So 13 cannot be there as a side of a triangle. And if you have 11, the minimum perimeter with 11 can be 11 plus 2 plus 3, which is 16. So 11 can also not be there. And with 2, 3, 5, 7, the only three numbers in arithmetic progression is 3, 5, 7. So this is our delta. So delta is 357 triangle. If A degree is the largest angle of delta and L its perimeter, determine this. Okay, so now the largest angle is the angle opposite to the largest side. So this is A. We can just apply cosine rule now. So by cosine rule, 7 square equals to 3 square plus 5 square minus 235 cosine A. This will be 49 equals to 9 plus 34 minus 30 cosine A. So this means cosine A will be minus 1 by 2. And since angles of a triangle are in the range of 0 degrees to 180 degrees, we know the only solution to this will be 120 minus 120 degrees. So A should be 120 degrees. And we have to find A by L. L is the perimeter divided by 15. This is 8. So the answer to this question is 8. So like there was not really like motivation for this question. This is like a very basic question, and like once you see the question, you just know what to do for this question. Okay. Uh so okay, that was an error. So this question says, consider the set of all 6-digit numbers consisting of only 3 digits A, B, C, where A, B, C are distinct. So we are given A not equals to B, not equals to C. Suppose the sum of all these numbers is something. What is the largest remainder when the 3-digit number ABC is divided by 100? So it says like what is the remainder when ABC is divided by 100, right? This is just basically BC. So we have to maximize this number BC in some way. So the thing is like you should like from this it should be clear that you will get some condition on A, B, and C, and using that condition you have to find the BC such that the number 10B plus C, like this BC, is maximum. Anyway, let's move on to the question. So let's assume that none of ABC is 0 for now. So we have 6 places. Suppose your A is here, and you have to calculate like what's the contribution to of this A in here in the total sum. So what can be the others, like what can be the 6-digit numbers which you can form when A is here? Like at this position you can place A, B, or C. So you have 3 choices. Here also you'll have 3 choices. 3, 3, 3, 3. You have 3 to the power 5 choices with A coming here. And the contribution of A in this position is A times 100. Similarly, B and C can also be here, right? So their contribution will be 3 to the power 5 times B into 100. So the total contribution with this place will be 3 to the power 5 times 100 times A plus B plus C. Now notice that we only consider this place. A, B, and C can also be at this place, like will also be at this place, this, and this. Like by symmetry, or you can like do it manually and show like when they're at this place, instead of 100 here, there'll be just be a 10 and everything else will remain same. So like in total, it will be 3 to the power 5 times A plus B plus C times 1, 0, 0, 0, 0, 0 plus 10,000 plus 1,000 plus 100 plus 10 plus 1. Yes, and this is equal to 1, 1, 1, 1, 1, 1. This is the total sum. And this is equals to this big number. 5, 9, 3, 999, 406. Okay. Calculations should not be hard. So let's cancel by 9. 54, 6, 53, 5, 45, 89, 9, 89, 9, 89, 9, 84, 9, 30, 3, 4. Let's cancel my 9 again. 63, 7, 29, 9, 9, 9, 9, 7, and what? Oh, sorry. 23, 5, 6. Yeah. And let's cancel by 3. It should be 2. Sorry, what? 2, 6, 6, 6, 6, 5, 2. Why is this 5? Yeah, I think I did a error while doing the division. 5, 9, 3, 9, 9, 9, 4, 6, 12. Yeah, this should not be common. Okay, let's do it again. 5939994. It does not really matter for the solution. I mean, for the explanation, but anyways, let's cancel by 3. So 1, 29, 9, 23, 7, 19.6, 19.6, 19.6, 4, 26. Okay, this is so dumb. Why am I not able to do the calculation? Okay. 29.9, 23.7, 29.9, 29.9, 29.9. Oh God. Okay, fine. Let's cancel this again, and this should be 6, 5, 9, 9, 9, 9, 3, 4. Okay, this is correct. 2, 1, 29. So it should be 9, 9, 9, 9, 7, 8, 7. I see the issue. Fine. 3, 3, 3, 3, 26. And then it should be 2, 4, 4, 4, 4, 4, 2. Yeah. So this should be equals to 1, 1, 1, 1, 1, 1 times a plus b plus c. And this is not easy to divide. This will be just be 22. Like here and then here. Okay. So we have a plus b plus c equals to 22. And remember, we have to maximize this number, bc. So like we can just take b equals to 9 and c equals to 9 and then a equals to 4. This is a possible solution. And then bc equals to 9, which is maximum. But notice that it says a, b, c are distinct. That is very important for the question. Because only then you can like say that there are three ways here. Okay. So so we cannot take 9, 9. So we can take b as 9 and c as 8. This is the second maximum thing. And in which b and c are like distinct. So 98. And then a is like 5, but you take modulo 100. So it does not matter. So it's just 98 anyways. So the answer to this is 98. Like you cannot get a number more than 98, right? So like this is the answer. But notice that we assume that none of ABC is 0. Like in a proof-based contest, you'd probably have to consider the case like when one of them is 0 as well. But that is like easy to do because, I mean, not hard to do because the thing you have to take care is when you're counting the number of ways to put a digit here, you only have two ways because you need digit numbers. But putting a 0 here will not make it a 6-digit number, right? And the contribution of a in the sum will just be 0. So these were the two things. Okay, anyways, but we have gotten the answer with just this assumption. And you need not do it in IOQM itself. So I hope the explanation was clear. Oh, this is one of my favorite questions in the test. I like this. In parallelogram ABCD, the longer side is twice the shorter side. So you have A, B, approximately half, C, D. If X, Y, Z, W be the quadrilateral formed by the internal angle bisectors. So X, well, let's just do this one. X, Y, Z, W. And we're given the area of this quadrilateral, we have to find the area of ABCD. Okay, like the first thing is, how do you even motivate? Like you're given area of this region and you're asked to find the area of this whole region, right? So one thing to notice is, okay, this thing is like, first thing, it's like, I think it's in 9th NCERT textbook, but even if you do not know this, it's like very easy to prove for a parallelogram. Like this should be the first thing you notice. Like, let's do something with angles because it's geometry, right? So let's say this angle is theta, and since it's like angle bisector, there should be theta. This whole angle should be like angle BAD should be 180 minus 2 theta. Wait, I'm recording, right? Yeah. Okay. No, man. So half of this angle will be 90 minus theta, and this is 90 minus theta. So this angle will be 90 degrees. So this is 90, and you can show that the all four angles is 90. So basically X, Y, Z, W is a rectangle. All right. So this is probably the first thing you notice, but what do you do after that? So, okay, also you can do this as well. Let's assume that WX is A and this length is B. Then you have AB equals to 10. Now, the thing is, uh, okay, how do I motivate this? Let's see. Yeah. Okay. So once you write these angles, right? Like theta, theta, 90 minus theta, like a common theme is similarity, like everyone knows that, right? And you sort of see that this triangle, do I have a marker in here? Mhm. Okay, never mind. So you see that this triangle has angle is theta 90 minus theta and 90, and so does this triangle. So it gives some sort of similarity in mind, right? Like which is sort of obvious. Like triangle, once it's obvious once you write the angles. Like it's kind of important to write the angles if you cannot visualize those. Like write all the angles which you see in the figure, and then it's easy to notice similarities. So triangle XDC is similar to triangle WDA. So XD by WD equals DC by DA equals XC by WA. So XD, and also we know that if this length is like L, then this is 2L. So you can see that here is AD, which is L, and here is DC, which is 2L. This ratio is 2 by 1. So this gives you that XD equals to 2 times WD, which means that this length XD is twice of WD, right? And you can write XD as XW plus WD. So twice of WD equals to XW plus WD, which means XW equals to WD. So which means that this length is also A. Also, from this thing, you get that XC equals to 2WA. So which means, okay, this length should be B because it's a rectangle. So XY equals to WZ. And using this thing, you can show that this length is also B. And by similarity, okay, not similarity, like by symmetry, this length should also be B. Okay, let's see. Symmetry is a powerful tool, right? Like, you know, parallelogram is a symmetric thing. Rectangle is a symmetric thing. So you try to find symmetries also so that you can reduce your work. If you do not like the idea of symmetry, you can like take what do you say? Similarity with triangle AZB and BYC, like do the same thing, just inverted, and you'll get that WZ equals to WA. Here, I'll just do it by similarity. Now, let's add another color. Nice color. Okay, I'll just do it. No mind. Okay, so now you see that this length is B and so is this length. This length is B, so is this length. This length is A, so is this length. So like these two are getting bisected, right? Like lengths about this point are equal and so are the angles. So you see another similarity, which is triangle. Oh, oops. AWD similar to triangle. This should be Z WX. Yeah. Okay. So now, you know that area of AWD over area of ZWX will be AW over ZW. Wait, is this correct? Yeah. So this should be AW is B. This is also B. So this is 1. So which means, oh, sorry, square of this thing. Which means AWD is equals to ZWX. And ZWX, like diagonals of a rectangle bisect the area. So this area is 5. So this area is also 5. And similarly, we know that this area will also be 5. Now, notice that like it should be clear that by symmetry you should have another similarity to find the area of DC as well. But if you do not see that, if you see triangle XWY and XBC, like you can see that WY is the midline, like joining the midpoints, right? So basically, like XWY, like WY is parallel to DC. So you can get similarity that way as well. Over XDC should be XW over XD square. This is 1 by 4. This means XWY is equals to, oh sorry, 4 times of XWY is equals to XDC. And XWY is again like 5. So this is 20. So XDC is 20. All right. So now the area will be, I'll probably raise some stuff. I do not want to go down. So you see A, B, C, D is ADW plus BYC. Okay, let's try to visualize this. Y, Z, W. So it's ADW, this area, plus BYC, plus this area, plus XDC, this whole area, plus ZAB, this area. And do you see that this rectangle is counted twice? So we subtracted once. So minus XWZY. So now we calculated ADW is 5, BYC is 5, XDC is calculated to be 20, plus this is also 20 by symmetry, minus 10. So this comes out to be 40. And this is your answer. Answer. Okay, let's move on to the next question. And this is my favorite questions from the test. Okay, not my favorite. My favorite is another question, but this is also one of the favorite questions. So you are given x, y, z are positive real numbers. You are given some 3 equations in x, y, and z. And you have to calculate this weird term. First, forget about the weird term. Let's try to get all the conclusions we can get from the given equations. So you see, this has a yz which has a coefficient 1. This is a xz which has a coefficient √3. So like it's like these equations are of the form, and you can say this is 0 yz. Like some a square plus b square plus something times ab equals to some constant, which in these cases are squares, 7 square, 6 square, 5 square, c square. Does this not remind you of cosine rule? C square equals to A square plus B square minus 2 cosine theta, angle between AB, times AB, right? It's just this equation. So now let's see. Suppose you have a point X. If you draw X and Y, sorry, you have a point P. You draw a length X from here and a length Y from here. And so see, in this case, it's 0xy, which means 0 equals to 2 cosine theta, which means theta is 90 degrees. So X and Y are at 90 degrees. And then this length must be 7. And the coefficient of y z is 1. So let's try to find the angle between y and z. So it's like minus 2 cosine theta equals to 1, which means cosine theta yz should be minus 1 by 2, which implies theta yz is 120 degrees. And you'll also get that cosine theta from this thing, zx is root 3, which means cosine theta zx is root 3 by 2 minus root 3 by 2, which gives theta zx to be equals to 210 degrees. And let theta xy equals to 90 degrees. Observe that these, oh, sorry, this is 150 degrees. I'm done. Observe that these three angles add up to 360 degrees. Which means if I draw a length here, Z, this angle I know is 120 degrees. Then this angle 150 degrees, and this satisfy that like angles about a point add up to 360 degrees, right? And now y and z, this length is 6 squared, so this length should be 6, and this length should be 5, like 5 squared from here. Okay, so now yeah, now you see you have a root 3yz, right? Like how do you get a root 3? Like sine or cosine is the motivation, right? So if you see yz, like this triangle in here, triangle BPC, the area of BPC is half yz sine 120 degrees, which is root 3 by 4 yz. Sure, there's a 4 around here, but we do get the root 3 yz for us, right? So like it motivates that we have to consider the area of this triangle, and this triangle. So let's see. APC will be, is just half, it's a right angle triangle. So it's half xy. This is xy by 2, which is 2xy by 4. And APB is xz by 2 times sine 150 degrees. And sine 50 is 1 by 2. So this is xz by 4. So if you notice, if I add all these three areas, APC plus CPB plus BPA, this will be APC is 2xy by 4 plus CPB is root 3 yz plus xz by 4. And this whole area is ABC. So now 4 times ABC is 2xy plus root 3 yz plus zx. This is the term which I have to calculate. So I just have to calculate area of ABC 4 times. And you know the side lengths of ABC, so you can use the Heron's formula. So let's see. ABC 5, 6, 11, 89 times 2 times 3 times 4. So this should be, oh, what? Oh yeah, P root 3. Okay. So this should be 3 into 2 root 6, which is 6 root 6. And 4 times of ABC is 24 root 6. And this is equals to P root Q. And we have to find P plus Q, which is 24 plus 6 equals to 30. So the answer to this question is 30. This was a lovely question, like realizing that you have to use cosine rule here, like find the angle between x, y, y, z, and zx. And you see that these things form a triangle. And realizing, like again, realizing that you have to calculate the areas of this triangle is kind of hard. Okay, so these are the first 6 questions. And now we'll move on to the next 6 questions.
Hello, I'm Siddharth. I'll be doing the second half of the paper, problems 7 through 12. Okay, so let's begin. So problem 7 is to find the number of functions f from 1 to 3, the set 1 to 3, to the set 1, 2, 3, 4, 5, such that whenever I is less than j, it gets mapped to stuff that's in that same order. Not strictly, just it basically the arrows can't intersect. So when you have 1, 2, 3, 1, 2, 3, 4, 5, you're mapping stuff such that the arrows cannot intersect. That's really all they're saying. How many ways are there to do this? Now, the main idea here, and this is an important idea throughout Olympiads, is that it sounds stupid, just like most important ideas, is that a sequence is just an ordered set, or like a sequence is just an ordered group of elements. That's all it is. So this sequence of f of 1, f of 2, f of 3, instead of thinking about it inside the sequence, think about going from the other hand side. You have some set of objects on the right-hand side, which are the outputs. And the condition that whenever I is less than j, f of I has to be less than equal to f of j, basically just says that whatever the outputs are, they should be fed into 1, 2, 3 in the same order. So we can choose the outputs first. So if you have, for example, 1, 3, 5, we immediately know what f has to be. F has to be 1 goes to 1, 2 goes to 3, 3 goes to 5, right? That the sequence f of 1, f of 2, f of 3 is just a set on the right side. And we're applying an order. And because of this condition, the order is fixed. And then, so now we're basically asking how many ways are there to choose the set, because each set gives a unique function. Now, as this example, for example, 1, 3, 5, that's a simple case. Because we have 3 different ones, it's just 5 choose 3. 5C3. So we have 5C3 ways to choose 3 distinct things, and each of those gives a function. But they don't necessarily have to be distinct. So for example, if all of them were 1, then you'd have to map everything to that 1. And there's 5 choose 1 ways to have that. There's 1 case left. You have 2 the same and 1 different. So imagine you chose 2 1s and 1 2. 2 1s and 1 2. Both 1 and 2 have to map to 1, and 3 has to map to 2. So we'd get 5 choose 2. But note that 2 1s and 1 2 and 2 1 and 1 1 and 2 2s, they're both counted by this. So we should have 2 up here. We're basically just counting the number of ways to choose 3 things from the right-hand side, the stuff on the right-hand side, the number of multi-sets of size 3. That's all we're doing. So this comes out to 5 choose 3, 10, plus 5 choose 1, 5, plus 2 times 5 choose 2, 20 is equal to 34. Hopefully that makes sense. It's just, just counting the multi-sets on the right-hand side. Instead of thinking from the left-hand side of orderedly, what can f of 1 be, f of 2, f of 3, the change in perspective is we basically just choose the output, and this condition of orderedness tells us immediately which output matches up with which input. Okay, let's move on to the second one. Okay, the second problem. You have any real number t, and this is defining the floor function. The floor function of a real number just tells us the largest integer below it. So suppose that n is the greatest integer, such that the floor of root of floor of root of floor of root of ugly stuff is equal to 4. So this is a problem where you don't really have to do much thinking. It's just walk forward with the definition they gave us. So most of the thinking is actually in counting the number of floors. Is equal to 4. So now apply the definition. Just don't get scared, apply the definition. We've basically just know that 4 is the largest integer that's below this. So then this has to be less than 5. Because if it was bigger than 5, then we'd have an issue, because then the floor would then be 5, right? Because 4 has to be the largest integer that's less than equal to t by the definition of the floor function in the beginning. So because this is less than 5, we can square both sides and we get that is less than 25. And this just tells us that because this is an integer, floor function is an integer, we know that this is at most 24. Okay. And now we basically have the same problem again, but one set of floor and root are gone. So we just continue like this. One thing to clearly see here is that because we're trying to choose the biggest n, it's good for us to just choose 24. Anything that's smaller will just give us a weaker bound, a smaller version for n in the next round, and we'll get a smaller thing. You can check, it's very easy to see. And now again, applying the same argument, we get that square root of floor of root of n is less than equal to 25. So it's strictly less than 25. And squaring both sides, we just get floor of n is less than 625. So then now we're at our last set. Root n is less than equal to 624. Sorry. Because again, the floor function is an integer, gives out an integer. Same argument again, root n has to be less than 625 square. So then this tells us that n has to be less than, apologies, n has to be less than the root. And so n is less than 625 squared minus 1. Make sense? And so now we just have to calculate what this is. And that's the largest value, because that works. You can just walk backwards. This would be just below the square root, like just below 625. So it would go to 624, which is just below 625. So it'll go to 25, and it will go to 24, and so on. And now we're calculating this is just, and once we calculate, we just have to get the sum of the digits. It's just answer extraction. And because the multiplication is hard, I multiply. See, I told you multiplication is hard. 9, 3, 0, 6, 2, 5. So hopefully I did the multiplication correctly, and you get 624. And adding, that's 9 plus 9, 18, 24. The sum of the digits is 24. Hopefully that made sense. It's just at each stage you do the same process. You just walk forwards with the same idea that you apply the definition of the floor function, you square, apply the definition of the floor function, you square, do it again and again, get the answer. Now we'll move on to the next problem. Okay, this one is quite interesting. So we define a sequence of points as follows. You start with 3, 1 and get the coordinates be xn and yn. At the start it's x0, y0. The next one, we define it with this set of equations, that xn plus 1 is minus 3 xn minus yn by 2 minus xn plus yn by 2 is yn plus 1. Just this linear equations in these two variables. And they're asking us to find the area of the quadrilateral formed by some points like far away, P96, P97, P98, P99. And when they do this, they give you this local recursion and they're asking you to find something very, very far away. They're basically just daring you to find an invariant. So a natural thing to try is the sum, the difference, maybe even the product. The linearity here would say probably product is weird. So we should try the sum of the difference. You can actually prove that the invariant would have to be something that's linear. But natural thing, just try the sum of the product. You can see that the sum doesn't really work. You get xn plus 1 plus yn plus 1 is equal to negative 2xn. Not very good. But xn plus 1 minus yn plus 1 is very good. You just literally get minus xn minus yn. This is just algebra. You can just check. You'd get this. And now this might seem somewhat magical to come up with the difference, but it's somewhat natural. That we want an invariant because of the type of problem that they're given. There's this somewhat random application, some random recursion, from one to the next is this random process to take to the next point. We should search for something that's moving in a constant way, we're moving in a simple way. And the sum and the difference are one of the two first things that you should check. Another natural way to come up with something like this is checking small cases. There's even some stronger patterns that hold that you can see quite clearly. So now this automatically tells us one thing, that xn plus 1 minus yn plus 1, or I don't know why I'm indexing that way, xn minus yn is equal to 2 times negative 1 to the n. Because for n equals 0, we had 2, and each time it's alternating in sign. So, okay, this is a lot of information. Now, because if you look at the equations that they gave us, we have xn plus 1 in terms of x and yn plus 1 in terms of x and yn. And the issue is that they're interlinked. You can't really, because we know how to solve equations in terms of one variable, xn plus 1 is equal to xn times something. We know how to solve that. So now that we have this relation between xn and yn, we can use that to then uninterlink these, to separate these in terms of just xn and just yn. And let's see what that gives us. So xn plus 1 is equal to minus 3xn, or to get at it quickly, 2xn plus xn minus yn. But we know what that is, 2 times negative 1 to the n by 2. And yn plus 1 is equal to negative xn minus yn plus 2yn by 2 is equal to 2yn plus 2 times negative 1 to the n by 2. And this clearly shows us what the pattern they were going for was. Because you see this random recursion, it's easy to get a little flustered or scared, but it's really just they're hiding something else. They're hiding some simple recursion with something much scarier. So now we just calculate, we just literally get that xn plus 1 is equal to minus xn minus negative 1 to the n. Now, at this point, we basically know exactly what each xn is. And I mentioned earlier that the pattern is actually stronger. It's quite easy to even see this exact pattern from actually calculating the points for small cases. Not that bad. But now we've proved it as well, because you don't extrapolate from 4 cases, because God is always watching. And now, from here, it's just, you can do it. Just think about what they're asking us at this point. We know that all points satisfy this equation. Xn minus yn is equal to 2 times negative 1 to the n. So in general, all points will satisfy one of two equations. Either y is equal to x minus 2 or y is equal to x plus 2. One of these two equations will be satisfied by all points. In fact, the points of the first parity, as in points that are even and with index even, will satisfy the first one, will satisfy this one. So for even points, and this for odd points. The parity doesn't really matter. And now we'll just think about what that means. We have figure, and we have the Cartesian axes, and you have y equals x minus 2 and y equals x plus 2. And we're going to choose points on this, and all the points are on these. So it starts P0 and then P1, P2. They're not specifically exactly over here. In fact, they invert and then -1, but they're always on here. So what does this tell us? That P96, P97, P98, and P99 also lie on these two parallels. And they go like P96, P97, not specifically here, the diagram is not to scale, and P99. And so if we had the lengths P97, P99, and P96, P98, we'd be done, right? Because it's a trapezoid, we know how to calculate that area. So let's try to get that, because we have basically everything we need to get that area. So calculating the area, we should want what is xn plus 2 minus xn, and what is yn plus 2 minus yn, right? Delta, that change, and those two changes, we square them, we add them, we get the length. So this first one is just yn plus 2 minus xn plus 2 minus xn. We write what xn plus 2 is in terms of xn plus 1. It's just minus xn plus 1 minus negative 1 to the n plus 1 minus xn. And write this below is equal to, again, writing it the other way, xn minus xn plus negative 1 to the n minus 1 to the n plus 1. This is just applying this equation twice to get from xn plus 2 to xn plus 1. And notice that these two cancel, and we get minus 1 to the n minus 1 to the n plus 1, which is just 2 times minus 1 to the n. Importantly, it has length 2. And because these two equations are the same, we can clearly see that yn plus 2 minus yn is also equal to 2 times negative 1 to the n. And therefore, what is the length of, so the length between pn plus 2, pn, this length is exactly xn plus 2 minus xn square plus yn plus 2 minus yn square root. And now we finish, because we know both those lengths. We directly get that the length is just 2 square plus 2 square root is equal to 2 root. So in fact, we get that it's not a trapezoid, we get that it's a parallelogram. So these two lengths are 2 root 2, and makes your life even easier. 2 root 2, 2 root 2. And the last piece of info we need is what is the length between these two lines? Not hard to get. We know that this length is 4, because this is x plus 2, this is x minus 2, y equals x plus 2, y equals x minus 2. This length is 4. We want the perpendicular distance, and we know that this angle is 45. So it's going to be 2 root 2, which is just 4 times tan 45, 2 root 2. So we get height is 2 root 2, length is 2 root 2, the area is 2 root 2 times 2 root 2, 8. So that's 2 root 2 squared is equal to, that's the area. Now, the main idea here was finding the invariant. Once you find the invariant, it's, I think, more direct. Maybe the idea of coming back to the initial equation can take a while, but I think once you spot this fact that xn minus yn changes simply, the problem kind of follows. I guess, realizing that those two equations are actually represent parallel lines, that can also maybe be a pressure point. But beyond that, I think it's quite nice. Problem is quite nice as well. So yeah, hopefully that was easy to understand. We'll move on to the next one. Okay. Now, like the 1-2 previous, the 8th problem, this one is another example of the problem where you just really have to walk forward. When I was trying this at first, I was overcomplicating a lot, but you just need to walk forward. So they said they want, suppose that p is the polynomial of least degree with integer coefficients, such that p of root 7 plus root 5 is equal to 2 root 7 minus root 5. And they asked us to find p of 2. And p of 2 is just an answer extraction. When I was trying it, I thought the fact that root 7 plus root 5 into root 7 minus root 5 equals 2 was important. It is not. They just wanted to find the polynomial. And so, yeah, we just literally just go from, they want the least degree, go from constant and up. Let's see what the least degree is. So can the polynomial be constant? No, because the right hand, because the integer polynomial, so you can't have a polynomial integer be equal to 2 root 7 minus root 5. So it can't be an integer. can it be linear? Again, no. This would have to be 0, first of all, and these two coefficients would be the same, but on the right hand side, they're inverted. One is negative, the other. So again, linear is not possible. Now, what if you add a quadratic, √7 plus √5 the whole square? Now the issue is that there's going to be a √35. When you expand this, you're getting a √35. There's no other √35. So A2 would have to be 0 and you're back at linear. And so again, squaring quadratic does not finish. And A3 √7 plus √5 the whole cube. Here, now at this point, this is good, right? Because you have a cube, and the cubes are the good thing about the cube expansion is that you don't get any √35s. You just get √7s and √5s. You don't get anything that's anything where you're crossing those two. And automatically, we know that A2 and A0 have to be 0 based on our earlier analysis. So we can just drop those two back immediately. And let's look at expanding this. √7 plus √5, the whole cube expands to 7 √7 plus 5 √5 plus 3 times √7 square times √5. So 21 √5 and √5 square plus times √7. So that's 3 times 5, 15 √7. This is what we get, 21 and 15. Now at this point, we have two different things, A1 and A2, any integers. We should be able to solve this. So let's look at what we get. A1 into √7 plus √. So let's look at the coefficients for √7. Let's group them. A1 plus 28 A3, right? And plus √5 into A1 plus 20 A3. So we just need to solve for this now. 2 √7 minus √5. So we get two equations. We get A1 plus 28 A3 is equal to 2, and A1 plus 20 A3 is equal to negative 2. So subtract them. 8 A3 is equal to 4. And I think I made a mistake, actually. Let me just check my calculations again. Yes, so the equations are wrong. So you can't add these two. One is √7, one is √5. Yeah, sorry about that. So you get √7 into A1 plus 7 plus 15, that's 22 A3, and √5 into A1 plus 26 A3. Yeah, this makes more sense. And yeah, it's much clearer why it works. 22 A3 is equal to 2, and A1 plus 26 A3 is equal to negative 2. As earlier, subtracting the 2, we get negative 4 A3 is equal to 4. This time, A3 is an integer, happily, equal to negative 1. Going back to the first equation of the second one, we get that A1 is equal to 22 plus 2, 24. So then the equation, the polynomial that we get, which is the smallest one, as we proved that all the smaller ones don't work, is then just negative x cubed plus 24x. This is P. P of x is equal to this. So then we can solve for P of 2, which is just negative 8 plus 48 is equal to 40. Okay. Hopefully that was clear, despite the error at the beginning. And here, there is really nothing to think about. It's just to not get scared by the statement and actually just look at the least degree. That's the main thing that we should learn from here, is that there is really nothing here that it looks a lot scarier than it actually is. You just have root 7, root 5. How can you add them and subtract them to get root 7, root 5? There isn't much more than that. There isn't much more structure than that. Okay, moving on to the 11th one. So you have a merry-go-round, a circle, and you have husbands and wives such that they're sitting alternatingly. So you have 4 husband spots and 4 wife spots. Let's call the husbands H1, H2, H3, H4. And W1, W2, W3, W4 for the wives. Now we're going to put, so let's say these are the husband spots. I'm circling them. The rest of the wife spots. Now the question is, how many ways are there to put them together such that no husband sits next to their wife? Again, this is, you just kind of walk forward. Because it's a circle, we're going to first have to anchor, basically just put someone somewhere and fix that so that everything else is relative to him, because otherwise you have the circle shifts. So let's just put H1 at this spot. And also note that choosing this one versus like this set of alternating vertices for the husbands doesn't make a difference either by circle shift, cyclic shift. So yeah, we're just choosing H1 at some spot, and that fixes where the husbands are going to be and where the wives are going to be. And now we can talk about it like normal, relative to H1, we know where everyone else will be. So how many ways are there to choose the husbands? 6 factorial, we have 3 spots, 3 husbands. You have, not 6 factorial, 6. 3 factorial is equal to 6 ways, right? Because you have 3 choices for this space. After you choose that 2, after you choose that 1. Classic idea. And so now let's imagine any general one. I'm just writing H2, H3, H4 just for explanation. For any general specific like thing like this, now we consider where the wives could be. Note that W1, whichever is the one, like W1 cannot be in either of these 2 spots. So then they must be opposite. There's 2 options for where W1 can be. And the thing to notice is that if W1 is here, for example, H2, one of its spots for his wife is already gone. W2 cannot be here, so it must be here. And similarly, H3's wife, W3, cannot be here, so it must be here. H4, W4 must be here. So it's literally just you look at where W1 can be, tells you where W2, W3, W4 is. Similarly, on the other side, choosing W1 would fix where everyone else is. W1 is here, we get that this position is fixed, and we get that this position is fixed, this position is fixed. And yeah, that's just it. So there's 2 choices of W1, each of them fix a certain cyclic permutation. So in total, we get 2 times 6 is equal to 12. 6 for the number of ways to put the men, and then 2 for the number of ways to put that first wife. Because after you choose the first wife, everyone else is fixed. And yeah, the main idea here, I would say, is the anchoring the cyclic permutation. Choose one person. I think that's a common mistake, is ignoring the cyclic shift. Just so immediately it's just anchoring it with some individual is just better with some object. Okay. I will move on to the next question. Yeah. So, okay, this one is a good question, but because it's computational, a lot of people got it without solving it. So the problem is you have a 12 by 12 board divided into 144 unit squares, and you're placing rooks such that you're just placing rooks, and they're said to be non-attacking if they don't attack each other. Very complicated lingo. And attacking meaning they're in the same line, just how rooks act normally. And they're asking, what is the least number of rooks that you can place, such that if anyone places n rooks on the board, there'll be some 7 of them that are pairwise non-attacking, such that any pair of them do not attack each other. So we're trying to find this number. And the immediate thing, and this immediate idea is why a lot of people got it correct without solving, is that we just try to construct. We try to pack a lot of rooks together such that like there are pairs that you can't get 7 rooks that are pairwise non-attacking. Basically that we don't want 7 different things. In general, any row, you're better off just putting more in there, right? Because you can't choose more than 2 in a row already. So why not just pack it? So when you're trying to construct, the natural idea is just to keep filling the rows down. If we fill 6 rows, then there still isn't any problem. So let's think about that. So we have 6 rows and all rooks. So that gives us 12 times 6 is equal to 72 rooks. 72 rooks on the top half of the board. There's no 7 that you can choose, because by PHP you choose any 7. Some 2 are in the same row, we're in trouble. And so yeah, 72 is naturally probably the maximum number of things that you can choose, such that there aren't one. So if you add any extra one, because if you add any extra one, we have an issue, right? We just choose some 6 and we add this one, right? But so we would be willing to probably bet a lot that 73 is the answer, and that's how a lot of people got it. Is just this construction. And for computational, that is enough. But again, God is watching. We'll try to prove it. So there are 2 main ideas here. I will show one that's more natural and then one that I like quite a bit. Is now the first one is just based on the construction. The construction basically tells us that like you're packing stuff into rows and you have 1 extra. So we'll naturally think about PHP on that fact that there's 1 extra. So we have 12 into 6 plus 1. We have 73 rooks, and we're trying to show that some 7 of them are pairwise non-attacking. 12 into 6 plus 1. And what our main idea is that a sum row, by the fact that 12 into 6 plus 1, some row has at least 7 rooks in it, right? Some row has at least 7. This is the PHP that we were building up to, the natural thing from 12 into 6 plus 1. And now the thing to notice here is that you have some line, some row specifically, with 7 spots that are rooks. Now imagine that we were able to choose 6 rooks from the rest of the rooks that are on the board. We are able to choose 6 somehow that are pairwise non-attacking. Then even if we draw those 6, they will knock out at most 6 things in this row. Like you choose this one, it knocks out 1, knocks out 1. At most 6 are knocked out by the 6 rooks. So there'll be some rook that's left over that's not attacked by any of those 6. We put those 7 together and we win. So we just want to show that there are some 6 left over, that there are 6 pairwise non-attacking rooks in the leftover configuration. And this kind of reminds us of induction. We're basically inducting down, right? Because we're removing at most 12 rooks, right? So we had 12 into 6 plus 1, and now we have at least 12 into 5 plus 1. And we want 6. Before we wanted 7, now we want 6. So this kind of inspires us to just induct. We have 12. We want to prove the statement that if you have 12k plus 1, we generalize, then we want k plus 1. That if you have 12k plus 1 rooks, there are some k plus 1 pairwise non-attacking rooks. And the base case of k equals 0 is clear. We just choose that rook, we win. So now we want to go from k to k plus 1. We've basically already shown the proof, but I'll show you more clearly. Going k to k plus 1, look at the fact that now we have 12 to k plus 1 in 12 rows. Some row contains k plus 2, right? Oh, sorry. Yeah, we're going from k plus 1 here, by the way. So in this case, we actually want k plus 2 rooks. We'll note that. So we have some row with k plus 2 rooks. Now delete all the rooks in that row. Now we're left with at least 12k plus 1, because we deleted at most 12. We have at least 12k plus 1 rooks. By inductive hypothesis, we can find some k that are pairwise non-attacking inside this. We can find k plus 1 actually. We can find k plus 1 things inside here that are pairwise non-attacking. Same argument as with 7. These knock out at most k plus 1. There is one left, and we just join them and we get k plus 2. So it's clear. We just induct each stage, there'll be one that's left, take it, keep going. And yeah, this just works. This proves the statement. And I think this is probably the more natural of the two proofs I was mentioning. This is the more natural one, because you're just thinking about 12 into 6 plus 1. This suggests a PHP. Some row, that's the natural statement that it suggests, is that you have 7 rooks in some row. And then from there, you're kind of deleting it and asking for the rest is reasonable. And the induction is also inspired by the fact that 7 is very random, given our construction here. Like, we can choose any k rooks, any k rows, and fill them with rooks. Our construction still works. So 7 is definitely random here. So generalizing to k and inducting is a natural idea. Now, the next idea I would just like to quickly mention is this idea of coloring, like shifting. Basically, you color like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's clear. You just color, you color in a straight line, and you just keep going. Like, you shift down. 1, 2, next row you start from 2, next row you start from 3, and so on. You can think about this in many ways. You can think about it as like the coordinates. If you have the coordinates like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have the coordinates for each square. You consider I plus j mod 12, and you color based on that, basically. And now we basically have to, we consider this coloring. It's a very common coloring in Olympiad math. Is this just, you can think about it as I plus j coloring, or you're just moving each time you're going one left. Is just to be clear, this is 12 and this is 1, color modulo 1. So then next time be 12.2 and so on. Hopefully that's here, it would be 11. That probably makes it clear what coloring I'm talking about. Just I'll make it a little more clear. You assign each row a number. So 0 to 11, 0 to 11, 0 to 11 is each column, 0 to 11 is each row. And you add those two, that sum, based on that you color. So if you have this this is in the ith row and the jth column, I plus j mod 12 is the color. Okay. So we color based on that. And if you just draw this, it's natural to see that no two ones or no two twos or no two things of the same color attack each other. So these are things that are entirely non-attacking, and there's 12 of each color. So you have 12 colors with 12 squares each. And importantly for a problem, each color is within itself is non-attacking. So we immediately get that we have 12 into 6 plus 1 by 12 ceiling. We have 12 into 6 plus 1 rooks going into 12 colors. Some color contains more than 6 rooks, right? By PHP. So we have 7 rooks that are in the same color. Those 7 work because the colors are not self-attacking. And that just finishes directly. And in general, for any idea of rooks attacking each other, this fact that this shifted coloring doesn't attack itself is quite nice. So yeah, this problem is quite nice, especially the part that many people, me included, during test I didn't do any of this. I just saw 73, wrote down 73. But I think during test, maybe not during test, no one would try to prove it. But if you're trying to prove it, I think induction is quite natural. And even the coloring, though maybe it's hard to come up with if you haven't seen it before, it's quite a very common idea. So yeah. Now we'll move on to a short analysis of the paper with me and Pranav.
Okay, so since now we are done with the problems, we'll do the analysis. The analysis will be like pretty casual. It's just like me and Siddharth discussing how the problems were. So it's not also we'll be discussing how hard the problem was. And you should keep in mind that the hardness is relative. Like what might seem easy to us might not be easy for you, and what might be hard for us might not be hard for you, right? And we'll mainly give focus on like niceness of the problem and like how nice the idea was. Okay, so let's see. So I think the first problem was like it's a similarity, and like I think most people would have just quad bashed this, right?
Yeah, quad bash. I think yeah, chord bash would be very common. Or you can do what I did and put L3 at the same place as
Yeah.
L1.
So what
Yeah.
Siddharth did in contest was you have like L1, L2, and it says are drawn in a place is the perpendicular distance between L1 and L2 is 3, and between L2 and L3 is also 3, right? So he just takes L3, like we take L3 here, right? But this person takes L3 here. It just coincides with L1. So now your square is like A, B, because this is like L1 and L3 both, C and D. And this is 3. So side of square is 3. So area of square is 9.
The answer is correct.
Yeah. I mean, technically it should be, right? Like, what do you think?
I emailed them, but they didn't listen. L1
Yeah.
equals L3 is just too much.
Yeah, but probably in like a computational, in a proof-based contest, we would have to consider that case, like as an edge case.
Yeah.
So like just for this edge case, I would say it's a decent proof-based competition question, but
I think the similarity is just. I think the similarity proof itself is quite easy to see if you just like if you have this just habit of marking all angles. I think it's natural to see it.
yeah.
Quad bash is also probably straightforward only. It's probably fine.
Yeah. Also, like similarity, it's like I think once you see that okay, this does not work, then if you are lazy, you would just draw on the same diagram. And you would think that okay, there's some tilt here. Like you will try to think about this tilt, right?
Also, I
So
think
that way
more
you
than
can
quad
motivate
bash,
it.
people would have trig bashed, which is basically just
Okay,
similarity.
yeah, that's true. Yeah. Okay.
Quad bash would be more complex.
Yeah. Second problem, I don't really have anything to say. It's just like observing that this is blue and then this is red. What do you think?
Yeah. Just yeah, if the biggest number is equal to the number of things, then it is the number of then it's all on the left. That's it.
Yeah. And also, I think a lot of people would have just like manually passed this. Okay, what if we have one blue pen, two blue pens, three blue pens?
I think this is one of those problems where like if you run, you'll get lost. Like if you
Yeah.
just think about what's actually being said, it's much easier.
I think I did this in contest when I gave this myself.
That impressive.
Fun fact, me and Siddharth both gave this IOQM, right?
Everyone gave this IOQ.
Oh yeah, everyone gave this IOQM. Fine. P is just a mindless problem. I mean, it's just probably like free marks.
Yeah, it's just do you know what cosine law is? That's
Yeah.
very interesting. And also, can you read?
Yeah.
Like,
And like not get scared by this line, like what when they define T
yeah, I don't.
and this.
Yeah, it's a little unnecessary.
Yeah. I think they just added that to like make people scared,
Yeah.
Okay.
I think they noticed
Problem.
that 357 has 120 degrees, and then they just like some problem they had to make with that.
That's true. And then they found this simple problem and then they're like, okay, what is the best way to make it scary? That. Okay. Fourth. I think it's like if you know basic computational combo, you would know how to do these kind of problems. No?
Yeah, I think it's doable. If you haven't seen the idea before, maybe it's a little confusing, like organizing the sum like this with each
Yeah.
A, B, C.
Yeah, so I think it's like if you have seen the idea, then it's doable. Otherwise, it's slightly clever.
Yes, I think it's
But again, like,
harder than
huh?
it's approximately the same as 2, maybe. The 2 you can really get lost, I feel like. But 2 and
How
4,
do you get lost?
like I feel like you can just basically do what you said. Like just if you don't notice the fact that all of the blue are on the left, it's hard to do the problem. So if you put R and then B, and then you just get confused. But that's really it. You have to notice that B is on the left.
Okay, that's fair. I see what you mean. Yeah. Yeah, you have to be on the right track, basically, is the point. And like, I think one idea is like, if you feel that this is going too long, then just know that IOQM is meant to be like doable and not like very long, unless it's like a 5 marker. In this paper, we do not talk about 5 markers, like a genuine 5 marker. This paper was a bad one. So, like, if it's a 5 marker, if it's not a 5 marker, it's not supposed to be that long. So, like, if you think that your approach is too much bashy, then it's probably not the right one. What do you think?
Yeah, but I think in general, trust HBCSE is like a good slogan.
Except 1 or 2 times.
To a good degree. Like it's not going to be terrible.
That's
Like
true.
I think going ahead, 6 is a great example of trust HBCSE.
Yeah. Okay. 5. I like the problem, like the idea of similar triangle. It's like heavily involved. So I think like it's not easy to spot it. Like when I gave the IOQM, I could not spot it myself. Like I drew this, I knew that this is a rectangle, but I was like, okay, what do you do after that? I did not try to find some similar triangles.
Hmm.
So I think one good
Makes
idea is like whenever you see a geometry is like try to find as many similar triangles or congruent triangles. Also write all the angles you know, no matter how messy the diagram is. If it's too messy, draw a bigger diagram. Like if you draw a bigger diagram, you can write as many angles as you want, right? Like theta, 90 minus theta. I think that makes it easier to
Yeah.
notice the similar triangles.
In computational, especially, similar triangles are king.
Yeah. Similar triangles and then
Especially
cycle
because
series.
they said longer side twice the shorter side. That's kind of like similar
Yeah,
triangle,
a
similar
length.
triangle.
Yeah. Yeah, like you by twice you would probably think like some midpoint theorem stuff. I mean, not always, but something. Okay. 6. What are your opinions? I want to hear yours.
6, like you have this cosine law motivation, but I feel like it's still very hard. Like I didn't get this in contest, obviously. I
Yeah,
think it's
same.
quite hard as you haven't seen the idea before. Like especially because like you look at it and you're just like, who wants to try this once you see this? Like,
Yeah, also one thing is I think you can get lost too is in finding what X and Y are.
Yeah.
Sorry, X, Y, Z. Which I don't think is possible to find. Like there can be infinite solutions, I believe.
I
Oh,
would
there
doubt it.
can't be. Yeah, there can't
Yeah,
be. But still, it's like I think very hard to find, right?
yeah, it's probably some like, extremely random sum.
Yeah. Like in our solution, we did not find X, Y, Z at any point.
Hmm.
Like maybe with once you draw the triangle, you can find X, Y, Z. Maybe that also.
I think you
Like
can, but
you,
it'll be like still very computationally heavy, and probably the answer is weird.
yeah. Oh, probably using barycenter you can.
Maybe.
Because yeah, like there's this thing with angles. Like if you're given a point P and you're given this angle, then you can write barycentric coordinates of P, like this angle and
Oh,
this angle. Something like that. I'm not 100% sure. But there it does exist.
it's
Oh,
basically
sorry,
circle.
not these angles. It's this angle and this angle, I think.
Oh,
But I
okay.
think still close enough. Like after a long bash, you can. But I think it's just better. Like once you get the triangle, you can still do the area thing. That is easier
Yeah, but
part.
once you get the triangle, like answer
Yeah.
extraction is there.
Yeah.
But yeah, that's I think the thing that if I think this is probably the problem with the least solves. I heard was this the one that you said was on some Allen worksheet?
No, it was some other problem.
Okay, but if it's not on Allen worksheet, I think this is probably the problem with the least solves because like I think this is yeah, if you don't come up with the idea, it's like you can get
Yeah.
lost.
I think 6 is the one with the least solves, and then probably like 5 would be the second least, I would guess.
Either 9 or 5. I feel like 9 might be that too.
9 was bonus. 9 was bonus, so it does not matter.
Oh, true. Very sad.
Yeah. Oh wait, I post share by mistake. Like you can see my screen, right?
Yeah.
Okay.
Okay, no, 7. 7, I feel like is just it's not too hard. It's just this idea that like ordered things are basic like any set you can order it. That's really it. Once you get that, you
Yeah.
can count it. I think a lot of people probably silly on this just
The
because
counting
it's
method.
not the number of
Like
sequences, it's the number of multisets. Like
yeah.
the difference between a sequence and a multiset can be subtle at times. So I think maybe that is the only thing. Other than that, I think it's relatively easy.
Also,
Just
maybe you
this
can
note,
like when you're
just noticing this that going from the
yeah.
right, that's it.
Also, another possible scope of errors which I found was like uh once you're taking the number of multisets, you can just do it as 5 cube.
Exactly. So that's sequence versus multisets. That's the number of
Oh
sequences,
yeah.
not the multi.
Yeah. And yeah, I think a lot of people would have solved this because not because of the method, because the values are too small. So you can just manually count that.
Oh, true. Yeah.
In contest, I manually did that. I'm like, okay, 1, 2, 3, 1, 2, 3, 4, 5. Okay, 1 is here. Then let's see how many things are there. And then yeah. So I think it's
I think
easier to
that even
manually count.
motivates the other thing. Like trying to manually count somewhat motivates it.
Yeah, I mean, if you have given like 1 to P here and to Q here, you try with base case and then you motivate that way. So I think it's the same thing. Okay, question here.
This one to me is somewhat silly. Like, it's just like, do it. I don't particularly like that. That's you have to find the square of 625. Like, that is too much
Yeah.
work. I cannot do long multiplication.
The thing was, I selected this in context because at last point I was like 625 square. Oh, okay. Instead of doing -1.
Yeah.
Yeah.
The questions like this is like it's almost on only computation. I feel like.
Yeah, it's probably better to not put such a question.
Yeah, if you're especially if you like, I guess the only way to get confused with this is if you haven't seen the floor function before. And
Yeah.
I feel like that's not a good thing to test even. Like, have you seen the floor function or not?
Yeah. And like floor of x is increasing as x increases. That tests this like
Yeah, true.
in a very stupid way. I mean, even if you don't know this, you'll just guess that, right?
Yeah, that's the math. Yeah. You feel it.
Yeah. Okay. This
This
was my
one,
favorite problem.
I like this one. And I think in contest, because you're like stressed out, you don't see the idea of like finding an invariant or anything. I think
Yeah.
like there's a general method to solve equations like these, and people probably just tried bashing, and that probably like the answer is probably very ugly. Hopefully the answer is not simple. I think I tried bashing, I didn't get it. So
No. I think bashing is not complicated. Like I remember in contest, I did not know how to solve these kind of problems, and I did not know invariants either. So I was like, okay, let's see 3,1 -4, -2, 5,3, and then with enough patience, you can just see that okay, what P96, 97, 99 be, and you can just use that like the shoelace formula.
and by bashing, I meant like setting up the matrices for going from x and y into xn plus 1 yn, and then finding the eigenvectors of that matrix. Like, there is a
Oh, the
general
linear algebra.
process for solving any equation like this.
They don't expect us to do that. I mean,
I know, but I was trying to scam them, but it didn't work. I think some people might have done this.
I don't think so. In IOQM, anyone would have done that, honestly.
Okay, maybe just me. One person tried doing this. I know one person tried doing this.
Except you?
No, me. I am the person. But the
Okay.
problem itself, I like quite a bit. Like, just subtracting,
yeah.
noticing the lines.
Yeah, this parallelogram idea was nice. Like I did not know this myself until I saw him tell that.
Yeah, I like that. I think it's also a good example of just trying random invariants, because I think in general invariants tend to seem kind of like magic, but it's just like you just try it. Like there's a finite number of possible invariants, because the invariant is not going to be like 26x plus 5y or something. It's going to be something simple.
Okay.
And for P10, I actually thought it would be much more complicated. Like I saw this, and I thought it would be like √7 minus √5 is equal to 2 by √7 plus √5, and then you take x to the other side, and you look for the minimal polynomial of √7 plus √5. Complicated stuff. But
I can see why you think that though.
Yeah, and Pranav told me, just check cases.
Yeah, also like the thing is, like it says least degree, right? So I think like the general vibe of people who are doing IOQM, like who haven't done Olympiads really, or you're just in a computational contest, your vibe is like just to bash it out. And IOQM has a lot of that vibe, I think. Or at least used to have in like past years. Not recently. I think like 2018-19 stuff.
Yeah, it is natural. Like I feel like to just check from small case. Especially because the answer can't be like more than 4, degree 4, right?
Yeah,
so like,
it's like very obvious that they won't put something which is more than 4. Like if they put something more than 4, it probably does not deserve to be here, and it's a better question. That's what I would think.
Yeah, but also like √7 plus √5, it can't be more than 4.
Yeah. Also, maybe like if you know too much, you'll try to like Lagrange interpolate. So like you'll try to find some other value, which is okay, maybe not, because you know how interpolation works though.
But you only know, finding some other value. But even then you need a third value. You need 4 values.
Oh, you need 4 values. Yeah, true. Oh, no, maybe the guess could be like, okay, since you only have one value, you can interpolate to get only one polynomial. But the catch there is like those are real polynomials, right? Reals are rationals. It's not valid over integers.
Oh, true.
So, yeah. 11th.
Okay. Yeah, 11th is straightforward. It's
Fun
pretty
fact,
sweet.
when I came back from the contest, someone told me that it was in their J worksheet. So they just remembered the answer of this problem.
Okay, this was the one. Okay, that's it's not as
Yeah.
bad then. I thought 6 was lost.
Ah,
11 was it's simple normal combi problem. Just
I think it's a
if you
decent counting.
yeah, it's just counted.
Yeah. 12 I like.
I think
Like,
a lot of this paper you can just say don't be too scared and try it. You'll get it. Like I feel
I
like
think
it's
that's true in
scarier than it
any
is.
IOQM, right? Like, just try to do the base case and we see, or not base
Exactly. Yeah.
direct case. That's what I was saying. The vibe of IOQM is bash.
Yeah.
Like, not the geometry or Barry bash, but like be courageous sort of bash, not the bash in the bad way. Well, I like this problem now.
Yes. The like I would be surprised if anyone even tried the back like actually proving it. But getting
Yeah.
73, I think, is natural.
Yeah, like I knew in contest that you can get 73 that way, but I was like, how do you prove it? I just left it. Like until I was solving the paper, like now for presenting, I did not think of that induction solution. In fact, you told me, right?
Yeah, but like I feel like everyone got it correct, but no one proved it.
Yeah. Like everyone got it, but nobody got it, sort of thing in contest.
Yeah.
Yeah. And by nobody, we do not include Pranjal. He also gave the contest.
Oh, yeah, true. Oh my God, he don't have IOQM.
Yeah, that's so. Yeah.
But yeah, this is a good problem. Like the whole problem, like proving it as well. I think it's nice. Just
Yeah, I
either
think
the
like if you
induction
remove
or
the
the
values,
coloring.
like some n cross n board, n squares, and then like by k rooks, then it's probably a nice problem. Nicer.
Yeah, and then like make it A, B, C, D, 4 options, JE style.
No, I would say you can put it in RMO as well. Like because
Oh
it's
yeah,
a
true.
proof
Maybe.
question, like RMO P1, I would say.
Maybe yeah.
I mean, not the answer. Like this original problem is easy for IOQM because you can just guess the answer this way. But if you have to prove it, then it's a good problem, I think. I would say.
Yeah,
Like I would
pretty good.
definitely recommend it. Yeah, overall the paper was like, I think not on the easy side, but not on the hard side as well. Like medium-ish. Like a lot of
Yeah.
questions are doable, but if you see the true solution of those, it's like some of them are really nice. Like to highlight once more, it's like problem 5, 6, 12.
I like 9 too. I like 9.
Yeah, 9 also. I forgot 9.
Yeah.
Yeah.
Hmm.
Okay, so that's
I
it
think
for
in
this
general, I
paper.
feel like
Huh?
if people were like told try all problems for at least 5 minutes, the number of scores would increase significantly for this. Like
I
if
think
they
the
were forced
contest
to
was
try it.
75 minutes long.
5 times 12. It works.
No, but you cannot guarantee that you solve in 5 minutes, no? Okay,
No,
maybe you
like
can.
I mean, like actually try it, like not like just try to think of it. Like actually try some small case, try something. I feel like people were
Yeah,
working
yeah.
much more.
Yeah, I think I remember like Vedant did perfect this paper, no?
Hmm. I don't know.
I think he got 40 out of 40. Yeah. No, not 100% sure though, but probably.
Lucky he cleared Haryana.
Yeah, our grade was 33. I just got 34.
Scary stuff.
Okay. I think that's it for this paper. Yeah. Thank you
Thank
for watching.
thank you.
Let me